Welcome back to Tronic Synergy. Last time we did a series of how to make logic units and arithmetic units. So we did an 8 by 1 logic unit, and then we did a 2-bit arithmetic unit able to do 6 different logic operations and 2 arithmetic operations, which were addition and subtraction. So next up, we were to start on registers, and that's what we are going to do today. We are going to start on registers, and we're going to understand what and what are these registers, how are they applied in the circuits that we have in modern days, what's their function, and how do they relate to the circuits that we did back then, like how registers are connected with ALUs, how they are connected with memory, and so on and so forth. So a register, simple definition of a register is just a group, it's just a memory cells which are connected together. A single memory cell is just a flip-flop. A single memory cell is just a flip-flop. And if you can remember, back then we did some few videos on how and a few different types of flip-flop. We did a set reset flip-flop, we did a data flip-flop. This is a data flip-flop that you're seeing here. We did a JK flip-flop, and so on and so forth. So for our circuit and our demonstration, we are going to majorly be looking at D flip-flop. So as we have said, a register is just a group of memory cells which are connected together, and a single memory cell is a D. Just say a single D flip-flop. Like this circuit is a single memory cell because it's able to store either 1 or 0. If I put 1 here and the clock is high, then definitely this Q output will be 1. If you put a 0 and the clock is high, then it's going to change that configuration, and this output will be 0. So this is a single memory cell because it's able to store either 1 or 0. And since we can store either 1 or 0, it means that when we connect these flip-flops together, like one here, another one here, another one there, and we connect them, then we are able to store like a 4-bit data, like let's say 1101. We can store something like this because we are able to store a single 1 using a single flip-flop. Then you can store another 1 using a single flip-flop. Then you can store a 0 using another flip-flop. Then finally we store a 1 using another flip-flop. So these are flip-flops which are connected together. So for those who forgot, or for those new viewers, let me just do a run through of how data flip-flops really function for us to understand and for us to get that basics on how this D flip-flop. This is going to be a very good foundation for you to be able to understand registers when you start working on registers. So this is a simple D flip-flop circuit. It contains a clock and it contains D data input. As those are the two inputs of the flip-flop. Okay, so let's say for example, we have our Q. Let's say Q is 0 and Q bar is 1. So this is a condition. Let's just put this configuration where we say that Q is 0 and the Q bar is 1. So leave that for a moment and let's come back here. So when, let's say, D is 0, we start off when D is 0. D is 0, the 0 enters here. Okay, then let's say the clock is high. We say that the clock, when the clock is high, it's when it's going to change the circuits to whatever it's in the data input. So when the clock is high, that is going to be connected here. You can see the connection. Then 0 and 1 in an NAND gate is going to give you a 1 output. The only time you're going to get a 0 output in a NAND gate is when both inputs are on. Since there's a 0 in the data, then it's going to give you a 1 output. that one is going to enter this NAND gate. Then the other input of this NAND gate is this one, Q bar, and the Q bar we say that is 1. So that one is going to come and enter here. So when they're 1 1 1 1, it's going to give you a 0, because we have said a NAND gate will only give you a 0 when both inputs are on. It's basically the opposite of a NAND gate. AND gate, basically the opposite of an AND gate. So when it gives 0, nothing really changes. It just remains 0, meaning that we are clearing the data. When if it could be a 1, then we clear it and we store a 0. So both inputs are on, it's a 0. Okay, let's check on this lower part of the circuit. So this 0, that 0 enters here. So this clock, remember we said that it's 1. So 1, it gives a 1 in this input. Then the data, remember we said that it's 0. So when it passes through an inverter, it's going to be 1. So 1 1, it's going to give you a 0. So this is a 0 and this is a 0. So we said it's only going to give you a 0 output when both inputs are 1. So because these inputs are 0, both of them is going to give you a 1 output. So nothing really changes in our circuit. Then let's take the next case. We want to store a data. So we input 1 in our data input. So that 1 enters here, and let's say it gets the clock when it's high. So the clock is high. So 1 1, it's going to give you a 0. It's going to give you a 0 in this NAND gate. This 0 enters here. Okay, and since Q bar was 1, so meaning that because there's a 1 and there's a 0, both inputs are not 1 1, then it's going to give you a 1 output. Okay, so when it gives you a 1 output, meaning that it has stored the data that you had put here. So that 1 enters this part of the circuit. So this is 1. Now let's check on this other end. So we say that this is 1, then this was 1, so it's going to be inverted to be 0. So this is going to give you a 1 output. Then so this NAND gate gives a 1, and there was a 1 here from the output. So 1 1 will give you a 0. So this Q bar is turned to 0. So this is 1 and this is 0. So we have set and we have stored our data. And even if we turn this off, nothing's going to change. If we turn this off, nothing is going to change until it gets the clock when it's high. When the clock is high, then it's going to change the circuits and it's going to store a 0. And that's basically how a D flip-flop functions. It functions when the clock is high. When the clock is high, it's when it changes the output of that flip-flop into whatever you had put at the input. So that's basically how a D flip-flop function, and that's how it operates. So for a register, we say that for just a group of memory cells. So this is a single memory cell. So for a register, we have a couple of a couple of those memory cells which are connected together. I don't know if you can see well. Just do like this. Yes. Just try to put this there. Yeah. We've said that for register, we have a couple of those memory cells which are connected together using the same clock. Yes, you can see it has those data inputs. So these are 4 bits, because this single one is going to be called a single bit, going to be called a 1 bit memory cell. So if it has 4, it's going to be a 4-bit memory cell, and it has 4-bit output there. So the clock is connected to each single flip-flop, so meaning that each flip will be getting the same clock pulse at the same time. There will be no delay. Okay, so this can be unclosed and it can be an IC parallel input, parallel output. I'm going to explain the different types of flip registers. Just for now, just understand these are parallel input, parallel output registers. We are going to go into even serial input and serial output. So how I've explained the memory cell right here. Let me now demonstrate it. This is a single memory cell. It is a single D flip-flop. I'm using AND gate here, NOT gate there. We have our clock signal here. This is an NE555 connected in oscillator mode, and we have the capacitor which is controlling the frequency at which we want the clock pulse to be. So these I'm using a 220 microfarad capacitor. It's much slower, but for a real-time circuit like a CPU or something else, these capacitors are very small, having a very small capacitance, because they measure the clock pulse is measured in nanoseconds. That's why when we want to type, when we want to do something in our computers, it's really, we want things to be really fast. So that's the speed of your computer. So basically this should be fast. It should process data very fast. So I'm using a very big capacitor. It's going to be much slower because I want to demonstrate and I want you to understand what I've explained there. So let me just turn this on and we can see. So it's on, and you can see the clock pulse. It's much slower. If it could be a real-time circuit, it could be very fast, blinking very fast. So we said that the circuit is controlled by this clock pulse. So when the clock is high, it's when the data is going to be changed in whatever you kept at the input. So if I put 1 in the input, it will have to wait until the clock is high for it to give an output. Okay, if I put a 0 here, it will have to wait for the clock to be high in order to change what was initially in the data flip-flop. Okay, so if I turn this on, I'll wait until it's off, then I turn it on, then you're going to see it's going to wait until the clock is high for it to give an output. So let's wait until the clock is off, then I'm going to turn. Now you can see, so it waits until the clock is high for it to give an output. So that's basically how. Then if I want to store a 0, then I will have to turn this off. Then I'm still going to time until the clock is high. I'm going to time the clock off, then I'm going to turn it off. Then you're going to see it has to wait for the clock for it to change what was initially there. So now, like that, you see, it waits until the clock is high for it to change the output. So we can do that again. So we're going to wait until the clock is low for us to turn this on. So let's see, it waits until the clock is high for it to change the output. Then we are going to turn it off. Now, like that. So it waits until the clock is high again to change the output. So basically our circuit is controlled by a clock pulse. So the clock pulse is what that controls our circuit mostly. So this is a very good introduction on how we are going to learn about registers. Next time we are going to check on different types of registers. We have serial input, serial output, serial input, parallel output, parallel input, serial output, and so on and so forth. And we are going to demonstrate them. We are going even to connect them. Then finally we can even connect an ALU to a register when we want to store that data. If we do an arithmetic operation and we want to store that data into a register, then we are going to do such kind of connections. So thank you very much guys for watching. Please subscribe to Tronics Energy, where we do fun stuff all time. So next time we are still continuing with our registers. This is a new series, so tune in all the time. Don't miss out on any episode for us to understand this concept well.